All right. Thanks, Josh. Really high praise. I hope I can live up to this high expectation. And also, thanks for organizing this. It's been great so far. So my name is Nate. My pronouns are he, him, his. And today I'm going to be talking about a deep learning computer vision pipeline that's able to recognize this very cute Animal Crossing profile picture of the character that just so happens to be me without a hat, and analyze a whole bunch of things about it. Let's see. Like it's a face. So our story starts when I got hired in 2017 at the Gina Davis Institute on Gender and Media. And as I got hired to one research team, another research team had just published this really interesting blog post about how they had built this tool that was able to analyze an entire film and draw boxes around all the characters, faces, and answer all these sorts of demographic questions in an aggregated sense. And it's a really great blog post. I put a little paragraph here, but two words in this blog post specifically stood out to me when I first read this. And that was right here, non-animated films. Turns out that this software was not able to actually analyze any films that had any sort of animated elements. And so when we look at the highest grossing films of 2019, that means at least 3 of these are going to be cut out for being completely animated. And the other 6 of them are going to be cut out because they feature animated characters like Thanos and Endgame, which means only Joker is the film that could be completely analyzed by this software. And this seems to be a really important design decision. And when I talked to the researchers about why they ended up making this decision, they told me that analyzing animated content is impossible, and a model just cannot generalize to new animated styles. And to even try to build something close to doing this, we need at least 2 million labeled images, which is a ton of data. And still, 3 years later, this quote sort of haunts me. Is it possible to actually analyze animated content? And today, I think I'm really excited to announce I've removed 2 characters from this quote, and I'm really excited to say it is indeed possible. But to do this, we have to make really conscious decisions about building the most generalizable model possible, and a lot of that comes down to the data. Now, as data scientists, I'm sure we can agree that data collection is often the most work of any side project. It's where many of my side projects have gone to die because collecting and labeling data is a very tedious process. And so the first thing I wanted to do was try to find a publicly available data set where I could just pull the data down and train a model with and start writing code day one. And the first thing I found was this data set. It's called Cartoon Set. It seems to be really great on the surface. There's a lot of data points. There's a lot of faces with different sorts of shapes and styles. This might have been a good choice, but maybe not for animation, because the truth is, the secret truth is that deep learning models are actually not very smart. So imagine we trained a deep learning model on this sort of data. So we can train it what a human is, and we can train it what an animal is, and we could train it on a whole bunch of data that's very similar to this. And eventually, it might get really, really good at predicting this sort of data. It'll recognize humans automatically and what animals are with complete ease, and our validation metrics will be through the roof. And we might think we've solved this impossible problem. But actually digging down into what the algorithm is doing, which is a little bit scary for deep learning models, but necessary, is we find that the model might think that all faces have to be facing the front and have these white, very clean backgrounds, which might not really be true of all our data. In fact, most of the data we might expect to see in the real world is not going to be this clean. So take this example of Mr. Krabs' daughter, Pearl, from SpongeBob, who has a single eye and a very large nose, if you can call it that, and an open mouth, and the model will just have no idea what this is. Because when we really dig down deep, we see that these left faces are really clean-cut, idealized versions of faces, but they don't match up to the real world where you can get an animated balloon and you can Sharpie a face on it, and that's the character, or have a frog looking sideways up in a medical examination room, or a man with oranges on his head. These are all valid character faces in the real world that our deep learning model would never be able to pick up on this sort of data. So I thought it was really useful to actually train the model on data that I hoped it would generalize well to. And that meant labeling a lot of my own data through popular children's and adult animated shows that had kind of interesting, diverse animation styles. Things like Apple and Onion, which is a show about a walking and talking apple and onion, to SpongeBob, which we've just talked about, has very weird characters, to, I think, the weirdest animation style of all, The Amazing World of Gumball, which is just crazy. In fact, I did a whole bunch of shows with very diverse, different animation styles. So these are all the shows I labeled for this data set. And it took many, many, many hours, but I ended up with a data set of about 3,500 hand-labeled faces. And for each of these faces, I not only drew a bounding box around where the image was, or where the face was in the image, but I also answered 4 classification questions that I hope to train models with. And these questions were animation style, whether it was computer generated or 2D, the category of the character, human, animal, or other, the hair color, and then if there was a human character, the skin tone on a 5-point scale that I adapted from Google. And so with this, I had data, I was ready to train some models, I thought I was good to go, but not quite. Because before you can even write a line of code, you have to really rethink the model. So let's look at an example from a classic film, Frozen 2. So imagine we're trying to collect this data from Frozen 2, and we want to go first with the character category. And so we might end up drawing these bounding boxes and labeling all the data for humans and animals and others. We do this for 3,500 faces, and then we take this data and we train a model with it. And that model might actually learn really useful generalizations about this data. So from the data alone, it might learn human faces have hair, which is mostly true. Animal faces have fur, which is mostly true. And maybe in the case of Olaf being other, non-human and non-animal, he has no face and or no hair and no fur. That's all really valid, great conclusions we want our model to learn. So then imagine we do this process again, this time for hair color. So we label yellow hair, brown hair, bald, other, and so on. And again, we use this data and we train a deep learning model to predict hair color. And again, it learns really useful things that would be important towards this prediction task. And then imagine we do this again and again and again for each one of the tasks that we want our model to train. And for each of the data sets we collect, we make entirely separate models. So we have maybe one for animation style, one for hair color, one for skin tone, one for the category, so on and so forth. And all of these are going to be trained separately. This is called the single task model architecture. And for a lot of deep learning algorithms and projects, this works surprisingly well. But maybe not for animation, because there's a really big problem with training using this architecture. So let's take an example here from the ice monster from Frozen. I think I'm just really obsessed with Frozen right now. So we take this monster, and all of these 4 models will be looking at this exact same image, but they'll all be coming up with their own sort of generalizations about it. So one might know one thing, one might know another thing, all based on the tasks that they have been predicted or been trained to predict. The problem is right here that all of these models look at the same image, they know separate things, but their knowledge gaps are actually completely region locked. They don't share any other information that that model might know with any other model. And we can see this might be a problem with an example like the blue model might be trained to look at hair color. And it might have really gotten good at hair color to the point where it learns it only needs to look at the top of the head, because at the top of the head is usually where hair goes. But imagine we feed it a character who might be bald and have sideburns, and that sideburns show the hair color and not the top of the head. And so the blue model might be really dangerously close to predicting the character is bald. But the purple model might be looking at data on the side of the face, or it might consider the whole face. And the purple model sees and understands the hair color on the sideburns. And if the blue model had that information, it could actually avoid misclassifying the character. And we can imagine these dependencies with the yellow and the green model, and the yellow and the purple and the green. In fact, I think it's a pretty fair generalization to say that all of these models would perform better if they had more information about the face. Ideally, we want to take this Venn diagram that's completely separate and merge it into the single, beautiful Venn diagram, where every model is able to share information before making a decision. And so what we're able to do is take the single task model architecture, and we can just knock it down. It's not going to work for this task. Instead, what we're going to need to consider is something called the multitask model. And basically, it expands the single task model by prepending a shared core network in front of it. And this shared core network is almost like the parent of a family of 4 task head children. And any good parent will know that all your children will want different things, but you're going to have to really prioritize what each child can do and try to find the best compromise so that every child can succeed. And in this case, that's kind of what the shared network does. It takes an image and it generates this really meaningful vector of numbers for each image. And that's called an embedding. And it sends that embedding or that vector of numbers to each of the task sets. So each of the task sets will get the same set of numbers for every image, but it's their job to use those numbers and add on some meaningful information from it to try to predict their task. So multitask models, it's really great, and there's a ton of benefits to them that I'm going to talk about real quick. The first is that we only need a single model to do all of our prediction tasks instead of many models. So we can think about many models like ResNets and Inceptions. They're often very big models, and maintaining them all, especially when there's a new PyTorch or TensorFlow version, is definitely a pain, and a single model is a lot better. It's a lot easier. Of course, as I mentioned before, tasks can share information, which is really great. The multitask model also introduces a more general model that reduces overfitting, because each of the task sets would like to optimize their data for the easiest way to get a prediction. So this might be like the hair color model learning to always look at the top of the head, but the multitask model, the shared core network in particular, doesn't let any model focus on what's convenient. It only focuses the model on what's important. And therefore the model, each task has to take in what's most important about the image, which is great. It helps us generalize towards new data, which is the goal. Of course, we're also able to generate really meaningful embeddings from the core network. And I'm going to go on a bit of a tangent here, but with no added cost, completely for free, a side effect of this is that our core network is so strong in generating these really meaningful vectors of numbers for each image that if we fed it a video, so in this case, an Animal Crossing video, we cropped out all the faces and we told the shared core network to find us similar faces to this using something like cosine similarity, we get an output like this. And this is an actual output from a model I trained. So you can see here the seed image on the top of our character. Despite changes in background, the model understands that they're very visually similar. The bottom character, even a change in headwear doesn't matter. The model understands through pose detection and all that the images are actually very similar. And just to kind of pass the gut check, we can look at least visually similar images and we can see humans aren't Tom Nook and Tom Nook is not a human. And I think that makes a lot of sense. So the last benefit, and also a pretty major one, is that the multitask model makes the object detection task a lot simpler. So consider this image from The Amazing World of Gumball, where you have 3 characters, and these 2 right characters, the orange and blue one respectively, kind of look like fish. They kind of might look like non-human, non-animal characters, and the object detection model might be sweating here because it has to make a decision whether it's animal or other. And so what it might do is draw the bounding box around the face, which is correct, but then label it with some sort of label with really low confidence. So this blue character on the right might get a 41% confidence. And then in post-processing, we might get rid of that face altogether because we don't want any sort of false positives. We want to reduce the number of low confidence bounding boxes. And this is a problem because right away, by doing this, we've missed a face entirely and we can't analyze that. But with the multitask model doing the heavy lifting, our object detection task is really able to look at a face and just have to determine if it's a face or a part of the background, not classifying anything. It's a very, very simple task, which means we get a lot more data out of this object detection, which is great. Okay, I feel like I have talked a ton. I've kind of teased the final pipeline. I've built up the components of this model that I think are really important. And finally, we can go through the final pipeline of the model for animated facial detection. So the way this works is we're going to start by inputting an image. In this case, it might be Tom Nook welcoming you to an island that's your new home, and also a world where you're going to be millions and millions of bells in debt. This image then passes through a fine-tuned, faster RCNN Inception object detection network, which consists of a few convolutional neural networks, and then finally passes through a final network that classifies whether it's just a face or it's part of the background. That's it, binary classification. And then we might end up with a bounding box like this, cropped around Tom Nook's face with a label saying it's a face, which is great. We're then going to crop that face so it's just the area inside the bounding box. We're going to send that through our fine-tuned ResNet 50, which is the core network to our multitask model, which then generates meaningful embeddings and sends that to each of the task head children, which all input this embedding and are able to generate a prediction from it. So in this case, for Tom Nook, it might know that the animation style is computer generated, the species is animal, the fur color is brown, so on and so forth. And so looking at the results based on an 85-15 random train test split on all the training data I showed you earlier of those shows, we can see that face detection mean average precision is 0.55, which doesn't sound great, but believe me when I say object detection metrics are really, really brutal. And so when we look at the 0.5 intersection over union, which is in that image below the second box, where the predicted box and the actual box are sort of overlapping, we can see our metric rises to about 0.89, which is actually really great. It's something to definitely be proud of here. When we look at the multitask model, this is accuracy, so it's a lot less math. It's easier to understand as humans. The animation style, the model is actually able to get fairly well with almost 100% accuracy, which is great. It's only a binary question. Character category, about 92% accuracy. And even though hair and fur color and skin tone had a lot of options, it was able to get about 85 and 80% respectively, which is really great. But none of this matters unless we're playing, we can analyze this model on a never before seen animation style. And so, Josh, if you can play that video, I actually ran the model on something that's very fitting to this conference, which is an Animal Crossing video. So the model has not seen this animation style before. Awesome, thank you. So the model hasn't seen this animation style at all before. I trained it with only TV shows. And so the fact that it's able to pick up on all of these characters, these cute villagers that are facing all sorts of different directions, all the Nooklings, these are what we would consider very non-traditional characters. And yet the model picks it up just fine. In fact, all these characters running around, the model fully understands that these are all valid faces, and it's a little hard to see, but they're actually with really high confidence metrics, which are really great. No, that's perfect. That's great. I'll move on real quick. So I ran these faces that the model detected. I cropped them. I took a screenshot every quarter of a second and ran it through the multitask model, and then compared it to what I would consider the correct answer. And we can see the animation style it got was computer generated with pretty high confidence. It thought some of the villagers were animals because I think they have very cute eyes, and the model might have learned to detect that. I'm not really sure, but it seemed okay. But the important thing to note is that hair and fur color and skin tone accuracy is relatively unchanged from this, a new animation style, to the content that I showed it during training and testing, which is proof that this model is actually able to generalize to new animation styles, which is really, really exciting. And so with this tool, we can do tons of really great things like copyright detection of animated faces in unauthorized content. We can enhance image search of animated characters. We can improve screen reader output by analyzing all the different attributes about a character and display this or explain this using audio for visually impaired, and so on and so forth. There's a ton of benefits to this sort of pipeline. And so wrapping up here, I know I'm a little bit out of time. I took this 2017 idea that was thought to be impossible and ended up making it actually really possible with only a fraction of the images, 3,500 images instead of 2 million. So I work at ShopRunner. We just open sourced the multitask model framework that we use in production. It's called Octopod. Just for fun, it's an animated sticker. I ran this through the model, and I'm actually very happy it got it completely right. It not only got all the faces, but understood these octopi were animals. It is completely open source. I highly encourage you, you should use it. It took me an hour to get all set up with the code. It's really great. I might be biased. I'm going to be open sourcing all my code and the data I've talked about here at my GitHub. I want to really quickly thank my partner, Jenna, for helping label so much of this data and not complaining too much. And my coworker / friend, Michael, who actually pushed me to finish this talk and help co-create Octopod, which is really great. So I'll leave my conclusion slide up during the Q&A, but thank you so much for listening to my presentation. It's been an honor. My video off? Oh, okay.
All right, and thanks for the talk. That was an awesome talk, and it was
Cool.
really cool to see.
If there's any questions, I can take them.
Yeah, that was a great talk. It was really cool to see. Let me turn your slideshow off. It's a great talk. Does anybody have questions, or any of you guys in the Zoom room have questions? I know you're all computer vision experts, so if you guys want to have a conversation about that last talk, feel free.
Do we ask now?
Yeah.
Okay, cool. Yeah, great talk. First question was, I mean, is it legal to kind of do this? Basically kind of take these Disney or these animated videos and draw a bounding box. I actually, the reason why I ask is like, I had kind of a similar idea, and I'm hoping that, basically I won't get into trouble if I even try this out. Did you kind of ascertain that it's actually like a legally valid process to do this?
I hope. I purchased all the content. I'm not making any money off of it. I'm not profiting. Right. There might be an issue, maybe open sourcing some of the data if this is illegal, but I'll take it down. But I think it's probably okay. I don't think I'm breaking any laws. If I am, I don't mean to.
Got it. Okay. Yeah, the second question was, there's been some work on the shape versus texture bias that CNN specifically suffered from, which is why you can kind of do these texture doping attacks and stuff like that. And there were some techniques used to kind of get the CNNs to focus more on the shape of the objects they're trying to detect or classify, rather than the color content or the textual content. I was wondering if you tried out any of these techniques.
I have not. This is pretty interesting. I'll look into it, but I haven't tried any of that. I think I mostly relied on just fine tuning some of these convolutional neural networks and kind of hoping that the deep learning model would be able to generalize from the data. I'll look into this. It sounds really interesting. Yeah. Maybe I can improve this even more.
Yeah, indeed. And in the similar vein, I think there's been a spurt of research on trying to find good confidence scores for face detection, because one of the failings of these YOLO or like these mask CNN type of approaches is that the detectors seem to do really bad on the corner of the images. And this is actually where, especially if you're trying to think of a self-driving car scenario, it becomes extremely important, because that is when the person is just about coming in through the edges of the image. He's just about entering the frame of measurement, and you want your classifier to be sensitive enough. So there are these very interesting packages like netcal, which basically take the softmax score, because softmax score is not really a confidence score. It's just a kind of a pseudo probability number that's masquerading around there as a probability score. So there are some very interesting Bayesian approaches like barbecue or Platt scaling that kind of take these softmax scores and turn them into actual rigorous CI values, or like these a posteriori probability scores. So it'd be a pretty cool add-on to have, so that every time there's a bounding box, you'll actually get to see like a probability score associated with it, and not using like the softmax as a proxy.
Yeah, that actually sounds great. There's definitely tons of room for improvement here. Yeah, that's great. I've recently calibrated some probability scores to get more accurately statistically confident scores. But I'll look into this method you talked about. Sounds really interesting.
Yeah, I just shared the link. I use this
perfect.
package, and full disclosure, it's not my package or anything of that sort. I just found it to be extremely well documented, and something that I've used, so it might be helpful for your project.
Great. Yeah, thank you so much.
Yeah, and yeah, thanks for a great talk. Looking forward to using it.
Awesome. Yeah, just a comment about the legality. From what I've heard, at least my experience with text, is that as long as you didn't need an account to get the data, then it doesn't matter what the terms of service was for the website. You can use the data and scrape it and use it to make a model and even open source the model, and there's no issue with that. And I feel like if you just find animations that have been legally posted online and you don't need an account to download it, then you can probably use it and distribute it. Like it's not like you're taking like the voice of children or the voice or image of unconsenting people. So I think
Yes.
as long as you can scrape the data without an account, you're fine.
Perfect. Okay.
All right.
Phew.
Well, thanks for the talk, Nathan. That was awesome. Next is Devin. So can you come up, Devin and Nathan?